go out. I mean, it sounds kind of backwards, but going outside a lot.
Yeah, I don't think that's backward at all. I think that there's like a weird distorted message that's like, stay in your house. No, social
Stay away
distance.
from other people.
Yeah, stay
Yeah.
away from other people. Yes, but all right, there we go. We're live right there. Yeah, stay away from other people. But it turns out that sunlight, social
Stay away
distance.
from other people.
Yeah, stay away from other people. Yes. Okay, I'm dropping the link, by the way, into the Discord channel. Sorry for that delay. Okay, there's the live link for anyone that wants to check it out on YouTube. No, stay away from people, but you get outside. The heat will kill COVID. Sunlight will kill COVID. You know, one of the best things you can actually do is get the heck outside, keep your distance. But you know,
And are you
Yeah.
you also streaming on Discord now?
I will be in a moment.
Okay. I just didn't know if you.
Yeah, no. Well,
that.
I have forgotten in the past, so there's that, right? So hang on a second. We are coming online.
There it is.
Bring. I'm going to blow that up. I'm going to go over here. I'm going to fix my hair. Okay. Oh, man. Let's see. Okay, so, yeah, no, going outside, seriously, that is a great, it's also just healthy for you, vitamin D, get some sunlight, don't burn yourself, and get skin cancer. But you know what I mean?
Fall off a mountain. I
Don't
go rock climbing when I go outside.
Don't fall off a mountain, for crying out loud. No, but it's really, I mean, also physically healthy, right? Just, man, I think that's great. And I think that the idea is not to hunker down in your basement like me, but to get outside. That is the ideal. In fact, my own view is that some of the like hyper, you know, there have been, back in the early days of this whole crisis, I'm pulling up all my stuff here, but in the early days of the crisis, there were a lot of things about, you know, it just seemed like you know, if you're like on the street or something, or, you know, or just
Conflicting.
hiking by
messages.
yourself, yeah, really bad messaging, right? Like, you go get in the basement with the other people where you can, you know, infect each other. You know what I mean? Anyway, that's my own opinion. But apart from all that, there's an emotional component. There's an emotional cost to all this stuff, right? And so, you know what I'm trying to say. So you've got to be careful to take care of yourself emotionally as well. Okay, we are right here. We did assign magnitude. Okay, I'm pulling this up. I'm going live. Crap, man, it's 10 after. Do we have somebody non-muted? Unless that was directed at me, in which case it's a little disturbing. Whatever that was. Okay. Let me see. Yes. Okay. All right. I just listed my home for sale. I'm going airplane mode on my phone because the phone's been ringing off the hook. There's no hook anymore, but the metaphor still works, right? Okay. Are we ready? Ready to rock and roll? But do take care of yourselves. Do take care of yourselves. Not just physically, but also emotionally. There's just a big toll. And then those two are intertwined. Physical and emotional. You know, if you're struggling emotionally, it takes a toll physically. And vice versa. So take care of yourselves. I worry about you. Okay, let's rock and roll. Let's do this thing. We had gotten to, we talked sign magnitude, right? And does that sound, I think that's where we got, right? Did we get this far? Hang on a second. I feel like we got right to here.
Yeah, we ended up around here.
We can look it up. But we talked about the range, right? of sign magnitude. Let me just say one thing. Let me just pound on something very, very important, which is that, and I've talked to a couple of you just, individually. These are notations, okay? A notation is like a social contract, all right? I cannot overstate this, so I'm going to try to make this pound into your head. Social contract, okay? Everybody with me? Social contract. What I mean by that is, a note. The bits are just bits. They mean whatever we say they mean, right? By the way, I apologize for the dunking Oreo and whiskey. It just was like current mood. It relates to our to our struggles, I think, sometimes. We get really disoriented with life in this weird new reality. The zeros and the ones mean whatever we say they mean. And the individual zeros and ones mean whatever we say they mean. So when we get to two's complement especially, some of you are going to have, I don't know where this gets in your head, but it's just bad. It's non-helpful, which is this. You'll say, and then you take the two's complement of it. Okay? Can you just not do that? Don't say that. Get that idea out of your head. Signed magnitude is a notation, which means it's a social contract for everybody looking at it. So when I go, that's signed magnitude notation, you go, oh, I know what the social contract on signed magnitude is, right? The social contract is that the leftmost bit, aka the high order bit, is the sign, and a zero means one. A zero means one. No, a zero means positive, and a one means negative. Right? And everything else is just a magnitude of binary numbers in base 2. Boom. That's the contract. So therefore, the biggest number that's a positive number is plus 127, which is just these, 1, 2, 4, 8, 16, 32, 64 all added together, get you 127. All right? And then this guy here, negative. Same thing, biggest number, negative 127. It's a social contract. We don't take the signed magnitude of something. Okay? You don't do that. Two's complement is a social contract. It's a notation. Okay? Everybody with me on this?
Yup.
Okay. Thank you for the yup. Somebody's got to say it. And just a little bit of feedback helps me to know if everybody's, if we're kind of like on board. You know what I mean? Okay, let's keep going. Does it occur to you that you could pretty much use any bit pattern to represent a number? I don't know what we just did. We didn't throw away the social contract. What did we do? Oh man, now I'm worried. We did kind of throw away we threw away the word social contract for effect.
The representation of the social construct, or social contract, was thrown away.
Yeah. The representation of the word social contract. Anyway, but does it occur to you?
Yeah.
Does it occur to you that that you could use any bit pattern to represent numbers? Why not just go totally random? Why do this thing? Any quick thoughts on that? What say you? Couldn't be on chat. There is chaos in the chat. It's breaking down rapidly. But either voice, the audio, or on chat. What do you think?
I have a guess.
Yeah, go for it.
Because you could use are you asking about bits specifically?
Yeah. Why do we could use any bit pattern to say that's a 5, that's a 42.
Well, in terms of bits, 0 and 1, we use binary specifically because it can represent true or false, or just it can represent basically information that computers can read and understand because of the electricity and the way that digital logic branches out. And then for like the way that we represent stuff in computer space later on, you're going to be talking about two's complement. And we use any sort of complement because it's easier for the computer to interpret, and it's easier to do. It basically like arithmetic, standard arithmetic works out well, where any sort of numbers within a certain bit pattern or within a certain amount of bits will just be able to be represented easier. Likewise, with that, if you have like sign magnitude or one's complement, those represent 0 in two ways, with a positive 0 and negative 0. But for two's complement, we use that because there's only one 0, so you can have a higher range of numbers, and the math works out easier.
Yeah, great thoughts, and thanks for just taking a stab at it. The biggest thing really is, there's really one point, which is we could make any combination of bits be anything we wanted it to be, right? I could randomly scramble the bits and say, we're just going to say that one's 83. Scramble them again. That one's 84. The problem is that the circuitry you'd have to do would just be absurd. Well, here's the thing, David. You said the math doesn't work. No, the math works if we build circuitry to take this random combo that we call 83 and that other random combo. You know what I mean? We can build circuitry to make those work. But why? But it becomes crazy complex. You see what I mean? That's really the idea. And if you build go.
Would it be for they're represented due to the fact of simplification, just for simplification purposes, so not make it so complex?
No, I think that's well, right. It's really two things: simplification, but at some level, you've got to actually build the hardware. Like I could build hardware, I could build circuitry that literally said this random bits, which we'll call 83, and that random bits called 84. When you subtract those two, that you get this random set of bits, which we'll call 1, and I could build a system that would work like that. It would be obscenely complex, difficult to understand, difficult to maintain, right? Difficult to build. It turns out that not if you just simply say, look, let's just start with binary numbers and normal binary counting. Just binary numbers as we know. There is a thing called base 2, right? Which we already know. If we start with that, and then we do as few tricks as we have to. We only do the tricks we have to, like leftmost bit is not the 128 spot. The leftmost bit is plus or minus. That's a little trick, right? That's a random. I mean, we could put that anywhere. We just had to decide how to do that, right? And so, at the end of the day, it's about simplification from a design perspective, from an implementation perspective, from a comprehension perspective. You have to maintain these systems. You have to build them. You have to understand them, okay? And maybe that's self-evident, but I want you to think about the fact that everything is at some level kind of arbitrary. You know what I mean? All these systems at some level are a little bit arbitrary. And they could have been a different thing. They could have been, we could have, instead of going lower to higher, right to left, might have been left to right. There's a lot of arbitrary things that show up here. And as I kind of mentioned before, the thing about computer science is that unlike physics, biology, they're really all about natural systems, right? Computer science is not about natural systems. It's about unnatural systems. It's about human-made systems, and so it's really a bizarre field in that respect. That almost once you get above electrons and semiconductors, and the fact that base 2 seems to be some kind of a mathematical law, the way we do number systems, and then everything else after that is just like arbitrary construct, and it leads to weird dynamics. You build this crazy database system, and then the client goes, "Can you make it fly?" And you're like, yes. Civil engineers don't deal with that. I love the bridge. It looks great. It works great. Can you make it fly? Civil engineers don't have to deal with that crap. CS, software developers, the client always wants it to fly or do something. And we're like, and then our answer is almost always, yes. Yes, we can. There you have it. Okay, let's keep going. So one's complement, where I'm at. So one's complement was it's not used. Okay, we're going to talk about one's complement as sort of a gateway to two's complement. Okay, there aren't, as far as I'm aware, there are no systems that actually use one's complement notation, but it's interesting and important as a point of reference to get to two's complement. Mike, yeah, you guys can discuss cloud storage and flying databases. I think there's something to be said for that. Actually, a database that flies might be, I don't know. I'm not even going to go there. I can't do it. Okay, so with one's complement notation, what we do is we take. Okay, I'm going to change my slide. You know why? Because I say take the sign magnitude, and I don't mean take the two's complement or take performing an action. That's not what I mean. I mean, here is a signed magnitude. Like take this number and now do the next thing. So I don't want take. What's my word? I'm just going to go look at the sign magnitude of a positive number. How about that?
Maybe use?
No. Because what I'm trying to say here is consider the signed magnitude of a positive number. That's kind of what I'm doing. I'm going to go with this for now. That this is still not right. You know what I mean? This is not what I want to say exactly. What if I do... let me see. Oh, I know. What about start with? Start with. You see what I mean? I didn't want to have this thing say. I just got done with a little speech about how you don't say, take the two's complement. You know what I mean? And then turn around and have a slide that says take the sign magnitude. It's not the same take. Does that make sense? It's not the same take. Start with sign magnitude of a positive number. And what I mean by that is the sign magnitude representation. Sorry, I'm going to do one more. You guys are hating me. You're like, Dr. K. But I think I'm home free now. I think I'm home free. The other thing, if I make a note to myself, like, fix slides later, then like when it's next semester and I'm on the same slide, I'm like, oh crap, I forgot to fix that slide. If I fix it right now, we got it. Start with sign magnitude representation of a positive. Is that better? I think that's better. You start with the sign magnitude representation of a positive number, okay? Or even an unsigned number, really. Yeah. I think this is a little confusing. It probably ought to just say unsigned, frankly. Anyway, one's complement is you just flip all the bits, that's the negative. Okay? Ta-da! Because the zero over here, right? That's the zero on the high end bit, right? Which says it's a positive. Flip all the bits, that becomes a negative. And all the other numbers are just the opposite of whatever they were. What do you think? That's one's complement. What do you think? Yay, nay? Up, down? Like? Not like?
I hate it so much. I
Looks
just
good.
Okay, we got I hate it so much it looks good. Awesome. Yeah, no, the interesting thing, let's take a look. Okay, yeah, the question was, do we still have negative zero? Okay, let's take a peek. So these would be the negatives, right? Well, would you have negative zero? And the answer, what do you guys think? Would we still have negative zero?
You would, wouldn't you? It's just all ones.
Right? I mean, I would start with positive, regular zero, normal zero, vanilla zero, would be all zeros. And when you flipped all the bits, that would be negative zero. Yeah, so you'd still have negative zero. So that would be positive 83, and that would be negative 83. You flip all the bits. Okay? Now, pros and cons. Ready? Pros and cons. Yeah, we're going to get back to negative zero, Andrew. Whether that's important, and it kind of is. But advantages, you still have the sign bit, right? That's nice. And it's actually fairly simple in the sense of converting between positive and negative numbers. Very simple, right? Flip all the bits, flip all the bits, right? And if I had that positive 83, if we go back, right, and I flip all the bits to get negative 83, how do I get back to positive 83? Flip all the bits. So every time I flip the bits, I'm just negating the number, right? Positive goes to negative, negative goes to positive.
Question.
Yeah.
With this one, you said still has a signed, signed, what was it, signed bit? The first one?
Yeah.
On the
Yeah.
left? Okay. Because I was going to ask, like, well then, if you just flip all the bits out, you are counting, and would be, if there wasn't something signed, it would be a representation of a negative number and a positive number. But that was because I was thinking there wasn't a sign.
Oh, gotcha. Right. If you didn't have a sign, you'd have this weird conflict.
Yeah.
Right, exactly. So now the interesting thing is that the circuitry required to do the negation is really simple, very simple. But when you actually get down to like doing math, the circuit logic is not as simple as we would want. Okay? That was kind of one of the motivations. But conceptually, it's really, really easy, don't you think? Now, I mean, is it easier than sign magnitude? You know, sign magnitude, you change the number only by flipping one bit. Boom, negative. Or boom, positive. Okay? But it turns out there's also some complexities with all of that, okay? But one's complement was sort of an experimentation, right? People started looking at. Now I'm going to do a little interlude. We're going to come back to counting in binary because this becomes, or come back to one's complement, because this becomes somewhat relevant. You have to become comfortable counting in binary to do all the rest of the stuff. Okay? Some of you already are. Some of you, your head's still kind of like melting a little bit. I recommend dunking Oreos in whiskey. Actually, I don't even drink. I don't even know what that is doing there. Current mood, that's all I can say. But the bottom one is one that we can definitely relate to. Counting in binary, okay? How do you count? How do you count in decimal? You know, counting is just adding one, isn't it? Isn't it just one? You know, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. It's adding 1. When you get to 9, 9 plus 1 is 10, aka 1, 0. Plus 1 is 11, plus 1 is 12, etc. It's exactly the same. Counting in binary is just adding 1 over and over and over, and then everything carries and ripples to the left. Okay? Are you ready to do it? Do you feel the need for speed? Here we go. That was 0, by the way. There's 1. There's 2. There's 3. 4. 5. I don't know how far this goes. 6. Goes to 6. Just because. Okay? Let's back it up. When you get to 1, you're trying to add 1 over here, right? You're going to add 1 there. And 1 plus 1 is what? 1 plus 1 is what? Let me ask, let's break
0.
it. Yep. Plus what else?
Plus.
Ripple the digit over.
Carry, that's right. Carry the 1.
Yeah,
Carry the 1.
that's what I meant.
Yeah, so like 9 plus 1 in decimal, we say 10, but what is it really? Like if you only looked at the column, 9 plus 1, what goes in that column?
0.
0. 9 plus 1 is 0. Carry the 1. You know? We just picked up one of that next power from the next column. Okay? So 1 plus 1 is 0. Carry the 1. So the 1 goes over here, and then 1 plus 0, the 1 drops down. That's 2. It also happens to be, no 1s, 1, 2, no 4s, no 8s, no 16s. That's also 2, right? Let me see. I was just reading the question from Braden. What if you do... Yeah, so the interesting thing here, Braden, if you add them, it turns out that addition in one's complement turns out to be a little clunky. Okay, so that's kind of the prelude. So Braden had asked, like if you look in the chat, there's a particular kind of question. And no, you're not overcomplicating it. It's just a little clunk. And we're going to move past 1's complement to get to 2's complement. But that's the idea. Okay, so then we add 1, which is 3. Ooh, what about this one? We add 1. 1 plus 1 is going to give us 0. Carry the 1. 1 plus 1 is going to give us 0. Carry the 1. And then 1 plus 0 is going to be 1. And we're going to get, that's going to be decimal 4, binary 1, 0, 0. Cool? Add 1, etc., 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 etc. You got to become comfortable just counting in binary and adding in binary. And those two are very, related. Okay? So what about this one? Are you ready? Let's do it. How do you solve this one? Binary addition. We just did counting, right? We just did, in decimal, we're going to, you count by adding by 1, right? 1 goes to 2, to 3, to 4, 5, 6, 7, 8, 9. We've got 10 digits. Well, in binary, you've only got 0 and 1. And so the only addition you're ever going to have is either 0 plus 0, 0 plus 1, 1 plus 0, which is the same thing, just upside down, and 1 plus 1. Those are the only options. And we just did all of those, really. We did all the 1 additions in counting. So it's basically the same. Cool. And do stop me if anybody gets confused or your head explodes or anything like that, or you feel your head turning to sludge. Go outside. Watch a live stream. Okay, there we go. So the 1 plus 0 gives us 1. Any carry? No carry. 1 plus 0. No, if we were going to draw this thing, there's like a 0. There's like an imaginary 0 up here for the carry. It's really 0 plus 1 plus 0. Which, if that just blew anybody's head, having 3 numbers you're adding in base 2, But there is an imaginary carry. So 1 plus 0 gives us 1. No carry. 0 plus 1 is 1. No carry. 1 plus 1, what's it going to give us? Anybody brave?
0.
And then carry what?
Carry the 1.
Right, so we go 0, carry the 1. Okay, now this is where your head explodes. 1 plus 1 plus 1, you're like 3.
1, but past the 0, right? Or past the 1.
Yep, it's 1. We'll say carry the 1.
Okay.
So that's the term, and we always know that means taking it into the next column. Just like you do in decimal arithmetic. Right? So 1 plus 1 plus 1 in binary is 1 carry the 1. Which, if you look at 1 carry the 1, this is my impersonation of 1 carry the 1. That's also binary 3, right? From your perspective, there's 1, 1, and there's 1, 2. 2 plus 1 is 3. This is binary 3. Okay. So, but the answer here is 1, and then we carry the 1. If there wasn't anything here, you'd notice that 1 would be there, and 1, the 1 and 1 together would be 3, actually. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 0 gives us the 1, and 0 plus 0 is 0. Boom. Everybody cool?
That's pretty straightforward.
Binary addition. There you have it. Okay. Now, another interlude. A lot of interludes here. I think there may be too many interludes, right? Once you have a sequence of interludes, are you even interluding anymore? I don't even know for sure. It turns...
Nested interludes.
What's that?
They're just nested interludes.
They're nested, but they're more like sequential. I don't even know. I don't know. Anyway, so it turns out, and this is where our motivation is going to come for 2's complement. Turns out that if you're building, arithmetic circuitry in binary, that if you could add a positive number to its negative and get 0, that would be super handy. Now, do we have that already in decimal? What's positive 5 plus negative 5?
Well, 0, but That's just intuitive. I couldn't necessarily tell you if that's how the math works out.
Yeah, exactly. Because in decimal, we would just go, well, yeah, that's the rule. 5 minus 5, aka, positive 5 plus negative 5 is 0. That's the social contract. Where's that paper? That's the social contract, right? But it turns out if I can do that in binary, where I take the positive representation of the number and the negative representation of the number, and basically just do like this, just do binary addition and have it become 0, that would be really, really great. Okay? So you can kind of feel the intuition of that a little bit, right?
Oh wait, were you saying that this is like adding the negative and a positive for one's complement, making it 0 is kind of intuitive?
No. I'm saying that independent of the notation, if you can add a positive to its own negative and get 0 while doing binary arithmetic, that would be ideal.
But we can't.
One's complement is not going to do it for us, and neither is sign magnitude. So let's take a peek. Let's do sign magnitude, okay? There we go. There's positive 43 and negative 43. Let's just, and I think I'm jumping, let me see. I'm going to go back this way. So what we're going to do is 1 plus 1 is 0. Good with that, right? We're just going to do this in our heads. 1 and 1 is 0, carry the 1. 1 plus 1 plus 1 is, anybody want to just say it out loud?
0.
It's 1 carry the 1, right?
Yeah, it's 1 carry the 1. This is my remote threatening for that answer. Yeah, no, it's 1 carry the 1. So all of a sudden you got a 1 down here in your answer. It's like, okay, can that possibly be 0? No. So we're already dumb. No, it doesn't work. If you just straight up add these, but that's not a shocker because really all we had was positive 43 and another positive 43 and then a sign bit. So we're really going to get is negative 86. You know what I mean? You see it, right?
Yeah.
I mean, it's really just positive sign, positive 83, negative sign, 43, negative sign, negative 43. Adding them together, it never was destined to work. Okay? Now, one's complement feels like, no, wait. We've got, the flipping of the bits. That feels like something is going to happen. Let's do it again. There's positive 43 in one's complement, and there's negative 43. What are we going to get? Anybody? You have to do this one off the top of your head. Take a peek.
All
What's it going to
ones.
be? It's going to be all ones. Every column, the answer is 1 plus 0. And what is all ones?
Not 0. Negative 0.
It's negative 0. Is that 0? Poor negative 0. He wants to be like the other zeros.
But he's not quite.
But he's not quite like the other zeros. And what do you do with that? And then now do you have to always convert negative 0 to positive 0? You know what I mean? Which one do you get to use if you just want to use a 0 for something? See what I mean? It's a mess. So, the question then becomes, okay, look at this right here. This is one's complement. Take that answer of all ones. What would you have to do? What simple act could you do? And I can think of 2 of them. What simple act could you do to convert that into straight up 0, where there was 8 bits of 0? What do you think? There are 2 ways I can think of doing it. So yeah, David said flip the bits. That's one. And then Isaac said add 1. Right, these are the 2 ways. Now, flipping the bits does, if we pop out the other side and we flip all the bits, but that, we'd have to know that that's negative 0. That's like a conversion of negative 0 to 0. We'd have to know that special case. What if we just add 1? Now, the key is, and notice the little bullet down here, what if you ignore the extra carry? Because if we start adding 1, you get 0 carry the 1, 0 carry the 1, 0 carry the 1, all the way, and everybody turns to zeros, but then there's a carry in the 9th bit. So if you ignored the carry, that would actually do the trick. And this was kind of the thought process. Like, well, what would I have to do to a ones complement answer to turn it into a straight up 0? Well, if I added 1, that would do it. So let's experiment with that. And they started to experiment with circuitry and stuff. And this actually led to 2's complement. Okay? This is the coolest thing that's going to happen to your life in the next 5 minutes. Hopefully you can do better than this in the evening, and hopefully you had something better than this in your morning, okay? But I'm just saying this is really kind of freak. It's weirdly miraculous, I guess, is the bottom line. The downside is you have to remember it. That's the downside. But once you get it, it's going to be the cool. Okay, so here's what you do in sign magnitude. In 2's complement notation. I was looking at the GIF. For some of you, I was looking at the GIF. But I was looking at the GIF, and it distracted me. 2's complement notation. Okay? To change the sign of a number, you flip all the bits and you add 1. This was like, you're like, well, when I did that last part, you know, I got -0 and I added 1, I got 0. What if I just made all negative numbers that same way? I take a positive number, and to make it negative, what would happen if I flipped all the bits and I added 1 and ignored the carry? Okay, then what if I took that negative number, flipped all the bits and added 1 and ignored the carry? That was the experimentation, okay? So let's do it. Let's do it, okay? Here comes positive 83. If you want to do that in your head, I got a 1, a 2. So that's 3 if you're doing it in your head. I got no 4s, no 8s. I got a 16. I got no 32s, and I got a 64. 64 plus 16 is somebody.
80.
80, thank you. And then plus 3, 83. Okay. I flip all the bits. That part's easy, right? I flip all the bits and I add 1. What do I get? If you do it, you know what I mean. I just add 1. It's basically the 1 plus 0 is 1, no carry. So everything is just the same. That's the representation of negative 83 in 2's complement notation. You can't really look at it and see, you know, like sign magnitude, you could look at it and go, oh, it's 83 and there's a negative. You can't really look at this and see 83.
With with 2's complement, is that last bits, or the very leftmost bit, still a signed bit?
Yep.
Okay.
But the difference between that and sign magnitude is the rest of it doesn't have like independent meaning.
Okay.
You know what I mean? But it does tell us that that's a negative number.
Okay.
So yeah.
I was thinking the same thing again, or if there would be two, if it would mean two things.
Yeah. So there's
it's
still
not 124. It's just a negative.
That's right. And it does mean, in effect, that you only have kind of 7 bits of, call it magnitude, you know what I mean? 7 bits to work with for...
7 number bits. 1.
Yeah, 7 number bits, exactly. Okay. Now this is the part where everybody gets confused. And by everybody, I mean not everybody. But I do mean enough bodies that it's worth me burning your time to say it over and over and over again. What happens is, as soon as somebody goes, blah, 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 2's complement, and they start flipping all the bits and adding 1 to stuff. Like, it's like this like knee-jerk reaction. If I go, so this number is in 2's complement notation, flip all the bits and add, wait, did I say negate it? Did I say I want the negative version of this number? No, if I don't say, now if I say here's a number, it's in 2's complement notation, okay? Deep breathing. And then if I say, what's the negative, what's the negative of it? Okay, to to reverse the sign, I'd have to flip all the bits and add 1. That'll turn a positive into a negative and a negative into a positive in 2's complement notation. But that is not taking the 2's complement of something. 2's complement is not a representation, a method for making a negative number. 2's complement is the name we give to the notation. We could call it Fred. We could call it orange. We could call it zebra. Okay? We just call it 2's complement. And in 2's complement notation, this is how I negate numbers. Period. Period. Period.
So there's no such thing as taking the 2's complement.
No, it's bad notation.
Okay.
It's like saying, that number you got there, that decimal number 83. What's the negation of it? And you go, well, let me take the decimal of it.
Got it.
Here's a number in hexadecimal notation. Let me take the hex of it. You would never say that. I would say here's a hexadecimal number, or here's a decimal number. You know what I mean? And then I might say, I want you, or if I gave you a string of 1s and 0s and I said, what's the negative of this number? You should appropriately ask, what notation? Is it unsigned? Well, there is no negative. Is it 2's complement? I know how to take the negative of a 2's complement, right? Is it an ASCII character? There's no negative, right? Like, what's the notation? I'm now regretting that I threw this away. It's now all damaged.
We've repaired the social contract.
I have repaired the social contract, and I have added red snowflakes to the social contract. And I'm keeping it here nearby because I've realized now that I'm going to need it. I feel like we can fix this social contract. Okay. Are you with me on this? So, and the problem is when you say take the 2's complement, it just jacks with your brain because I say, okay, this is 2's complement notation. What do you hear? Take the 2's complement. No, just, it's like, how do you negate a positive number in decimal? You stick a minus sign, right? How do you make that negative number positive? You either erase the minus sign or draw a vertical line through it so it makes a plus, right? That's how you negate a number in decimal notation. You don't take the decimal of it. In 2's complement notation, you negate a binary number by flipping the bits and adding 1. And then this is really important. It might carry out. You only worry about the 8 bits. You ignore the carry. That's the weird thing in 2's complement. You just ignore the carry. Okay? If there's overflow, it's going to be, remember you've got 7 bits of kind of like magnitude, right? If it overflows, it's going to go overflowing into the sign bit. It'll mess with the sign. But stuff flowing out of the thing, you just have to, for now, just take me on faith that that's okay and it's all right and we ignore the carry out. Okay? So Andrew asked, in this notation, there must be a finite amount of possible numbers. Yeah, that's absolutely right. And the answer is, how many bits have you got? So if I say in this example we have right here, this, by the way, this is period. This is not the social contract. We're okay. But, okay.
Dr. K,
Yes.
would it be accurate to say that a relatively small positive number is going to look the same in signed magnitude, unsigned magnitude, 1's complement, and 2's complement? Like, let's say we have 8 bits, and the count we're trying to represent is, say, 13.
Yep.
13,
No.
Positive 13 is going to look the same for unsigned and signed magnitude and 1's complement and 2's complement The
Yep.
only difference comes when we want to represent negative numbers.
Giving you a big hand here. No, that's exactly right. That's exactly right. When it's a positive number, they all look the same. The unsigned, the ones complement, twos complement. And we'll look at other notations like ASCII and other kinds of stuff. They just all look the same. It's negative numbers. Now, here's the thing. So Andrew asked or made the comment, in this notation there must be a finite amount of possible numbers. Yes. And that's right, because otherwise you're like, if it were infinite, the carry out wouldn't matter. And if I say, like in a homework or a module exam, if I say, for example, look, here's just two binary numbers. They're just two binary numbers. I don't tell you anything about notation. Then the assumption is just that they're unsigned, right? Because if I don't tell you how to represent a negative number, there's no way to represent the negative number. We don't have a social contract. Okay? So if I just say, here's some numbers, 00110 plus 101. Just line them up and start adding. And if it's, if the biggest number was 8 bits and now you're 9 in the answer, that's all right, right? Like if I had 80 plus 25, I get 105 in decimal. I started with 2-digit numbers and I end with a 3, right? That's okay. But when I start to have to say, okay, this is 2's complement, I got to know how many bits there are, right? And so in this example, there are 8 bits. That's pretty standard for a single byte, but you might have 16 bits or 32 bits, but there you have to know how many bits there are, okay? That's just like one of the rules. And I think, Andrew, that you kind of intuited that by the idea that, well, if it's infinite, you can't ignore the carry because there is no carry out. Carry out means that there were 8 and now there's a 9th. That's a carry out. Okay? Now, okay, so David asked a really, really foundational question. Mike gave a partial answer. Sorry, Mike, it was only a partial answer. I'm giving you only this much of the hand. Just that much. Captain Partial, we need you. How does the computer know what notation is being used? Okay, you ready for this, David? Now, where's the social contract? This is beginning to be almost illegible, right? Yeah, you can.
It's a kosher contract.
It's a kosher contract. Exactly right. Okay, we're going to get to this. We're going to get to this in more detail. But it turns out if I'm writing some software, it all comes down to context. If I'm writing code and there's this data value, and I know that it's a number that can be positive or negative, right? It's a 2's complement number. Then I'm going to just treat it that way because I know what it is and all the code treats it that way. If I know that it's an unsigned 16-bit integer, then I know it because the code knows it. That's why I label it. Like if I were doing this in C or C++, I might just declare its type to be uint 16, or an unsigned integer. I know the type of these things, and I just have to sort of, deal with it accordingly. All right. A lot of you had Python before this, and a lot of you, that's your only programming experience. And I want to just say I love Python. I think Python is an amazing language. But what it does is protects you a little more than, say, C or C++ from having to know about things like data types. In C, you have to know how many bits your integer is. You have to define it. Like this is a 16-bit integer. It's an 8-bit integer. You know what I mean? So the types are much more in your face in C and C++. Okay, so I think Python's great for learning how to program, the structures and all that, but it does abstract you up. Remember abstraction? It does abstract you up so that you don't have to worry about all that detail, and it doesn't make you think about data types. that is both a strength and a weakness, mostly strength. But when you're trying to talk about hardware, it's, you don't necessarily have that point of reference. But when you write this program, the question is, how are you going to treat it? Like, for example, if I just gave you an 8-bit value and I said, okay, that's a 2's complement number. And then I said, what's its value? You would look at it and you'd go, oh, negative 83. I said, okay, nothing changed, same value. It's an ASCII value. Now I'm going to just tell you it's an ASCII value. What's its value? Capital Z. Great. Nothing changed. Now it's this value down there, let's say, that's on your slide. And it's an unsigned integer. It's an unsigned integer, 8 bits. What's its value? Well, we'd have to add it up, okay? But it's not going to be negative 83, right? It's going to be a positive value, right? If you want to do this, 1s, 2s, 4s, 8s, 16, 32, 64. So it's 128. If somebody wants to just run the numbers, 128, no 64s, plus 32. So what's that, 150? No 16s. I got an 8, so it's 158. I got a 4, so 162. And I got a 1, so 163. So if you so the very same bits, what do they mean? Well, Kochel contract, right? You tell me, is it an ASCII value? What if it actually means the value of the color? Maybe it means a particular color for a pixel, right? It's just data, and it means the color of a particular point on a monitor. Everybody with me on this? So, and that's why, David, it was a brilliant question. It's a great question. And this is the mind-blowing thing. The computer, when it's sitting in memory, when the value's sitting in memory, computer does not care. Doesn't care. Doesn't know, doesn't care. Right? It could be an address. It could be a memory address in that value. It could be anything. It could be anything. Okay? And it's only a question of how you decide to treat it. Any clarification of that? Because that's huge. That's actually very important. Okay? That idea is very important. And it's a little early, but that'll settle in. Okay, I'm going to keep going. All right. So we did this thing before where we started with a positive number and we negated it, right? Let's start with a negative number. Negative 83. Now, everybody kind of confirm, right? That's the number down there, right? 1010, 1101, 1010, 1101. Same number, negative 83. We flip all the bits and we add 1. Ready? Drum roll, please. This is going to be easy because it's basically just going to be all of that and then that, this guy's just going to 1 plus 0 is 1 and there's no carry. Okay? Now I'm going to back it up. 0101, 0011, 0101, 0011. There's that positive 83. Is that freaking anybody out for just a second? I take positive 83. I flip the bits and add 1. Boom, negative 83. I flip the bits and I add 1. Boom, positive 83. I can do this all day long. Flip the bits and add 1. Now, remember in 1's complement, flip the bits. You could keep doing that. And in sign magnitude, flip the sign bit. Just, you know what I mean? Just keep flipping the sign bit. But in 2's complement, flip the bits and add 1. Take that value, flip the bits and add 1. Do it all day long. That's kind of crazy. That's pretty cool. Agree with Andrew. It's actually really cool. So what it means is I don't have to worry about the weirdness. And as we're going to find out, spoiler, ready? No negative 0. 0 goes 0. Okay? Here, are you ready? Are you ready? Nah, two's complement doesn't really have any. Two's complement sticks. And this is why, by the way, there's no one's complement on the homework and no one's complement on the module exams. Okay? I want you to walk through it because it aids the process of thinking. But understand that it was a gateway to two's complement. Also, that's why we call it two's complement, because we called it one's complement and they added, it's almost like a bad sequel name. You know, Ready Player One, which was
complement to Electric Boogaloo.
Nah, exactly. I was going to go Ready Player One, which was an okay movie and a really great book. And then there's apparently a sequel coming out and it's called
Ready Player 2.
Ready Player 2. My impression is that two's complement was like one's complement, but we have to add one. See what we did there? Two's complement. It's a bit of an artifact. But if you understand that one's complement, that actually makes sense, right? Two's complement doesn't. It's a little confusing. Okay, are you ready for this? Now I think that my slide just dumps the answer, but let's do it. Let's do it. 1 plus 1. In fact, I'm going to go boom. Nope. Okay. There's negative 83. 1 plus 1 is 0. Carry the 1. 1 plus 1 is
0.
0. Carry the 1. 1 plus 1 is 1 plus 1. Right? It's just going to be the same thing every time. 1 plus 1, 0. Carry the 1. 1, 1, 0. 0. Carry the 1. 1, 0, 1. 0. Carry the 1. Until you get to the end. 1, 0, and 1, which is 0. Carry the 1 out and ignore it. And what have you got? All zeros. Sweet. And then this is the key, right? That guy right there, man, you got to ignore the carry out. You've got 8 bits. And this is the hardest part, besides the part where you realize that it's a notation, not an action. So don't take the two's complement. I swear to you, and not everybody's here and not everybody's going to watch this and you're going to try to fake it till you make it and it's not necessarily going to end well. But there's this thing that you guys will get really confused where somebody says, hey, Biff, two's complement. You're like, whoa, flip all the bits and add one. And, you go raggy and it's like, why are you going raggy right now? Look, I just said there was a notation that we call two's complement. If I ask you to negate a number, now do it. Within the context of this notation. All right? And so, yeah, David, so is all one still negative 0? No, it's not. Which is a great bit of thinking because you're now saying, well, what about all ones? What about that one? Let's talk about that, shall we? Oh, nice. Oh, I get it. Sorry, I didn't have the animation on the GIF, but yes. The cow. That's right. That's the carry. Ignore the cow. Ignore the carry. That's a fantastic. Thank you. This is just incredible. Okay. So, I kind of already talked about this. Modern computers use two's complement. Why did I pester you about all that? I explained it. I already got it. Okay, now, here's some tidbits. There's no negative 0. Okay, how would you prove it? How would you prove that there was no negative 0? Anybody? Bueller?
I would assume that there was a negative 0 and try to prove that there was and see what happened.
Yeah, but how would you do it? How would you prove it?
By proving that there isn't one?
No, that's the goal, not the I'm saying the goal is to prove it. Either that it is or that it isn't, but what's your process for proving?
Taking the negative of 0?
Right? That would be a good way. So first of all, let's start with the idea. And I don't think I have. I think I've
If you flip the bits and add 1 of 0, you just get 0.
Yeah, let's check it out. Let's check it out. Imagine, I'm going to do it this way, okay? I got 8 bits right here. Normally I would do this on the board, and I don't think I've adapted the slide for this. Okay, so here's 0, right? Everybody good with 0? You know? You're cool with that, right? So if I were going to take I've got to negate it, and it's 2's complement. What do? I flip all the bits, and then I add 1. Now, this is your the low order bit, right?
Yeah.
Yeah, it's on the right. Okay? I add 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1, 0, carry the 1. 0, carry the 1. It's starting to look like I'm going to get obscene. I'm not. And then there's like this carry out, but I don't care. I ignore it. What have I got?
0.
I'm back to 0. So if I take straight up 0 that we already know is 0, 8 zeros, I flip all the bits and add 1, and as long as I ignore the carry, when I'm done?
0.
0. There is no negative 0. You can't get there from here. You negate it, you get positive 0. You know, you negate it, you get vanilla 0. Let's call it vanilla 0. But the sign bit is positive. Okay. All right. That's kind of cool, right? I think that's really, really, really tight. And what it does, here's the thing. Remember when we were doing our little ones complement and we're just like, oh crap, negative 0. What do we do with that now? It doesn't look like positive 0. I can't use it the same way. The bits don't look right, and I got to remember. This is just like, no, as long as I've got a positive number and a negative number, or any 2 numbers in 2's complement, and I just straight up add them. I just straight up add them. It's going to work. That's just tight, in my view. So here's the question. You know you're going to have an extra number, right? We don't have negative 0. We said before that we had from negative 127 all the way up to negative 0, right? Then positive 0 to positive 127. We just picked up an extra value. Where are you going to put it? And it's kind of got to be on one end or the other, right? You're either going to pick up a positive 128 or a negative 128. Positive, negative. I don't know if I had that in the right order. My thing comes at me mirror image. No, mine comes right. No, mine comes actually the way you see it, the image I have. But it's like I'm looking at myself, so it's not natural. What do you want? You get another number. Negative 128 or positive 128? Which one? What say you, my friends?
Personally, I would want an extra positive, but that's not the way they went.
Well, because you're a positive person. Naturally positive about life. Yeah, but what do you think? I mean, some of you have looked ahead and you kind of like, oh, yeah, I already saw the trailer. I know how it ends or whatever.
Well, it's going to be the negative 128, right? Because there is no negative 1 or negative 0. So that value with the sign bit being flipped to 1 would be...
Yeah, and then David asked this question, which is correct. We're talking about this value, right? In 1's complement, that was negative 0. So we're really talking about the same number, right? All the other numbers that we already kind of, talked about. But this one right here was the one at issue. How are you going to... What's its value? What's it going to be? There's one bit of intuition right now, which is, what's the sign on this thing?
Negative.
Right? I mean, if you're going to go, oh, that's positive 128. Oh, really? This bit begs to differ. Take it up with the high order bit, who says, most definitively, this is a negative number. And then you're like, well, we could build special circuitry, and we're back to that mess. Like, okay, if we just start with the natural assumption that it's negative 128, okay, then what do you do? Then you've got to try to, look at, what do you do with that? And we're going to walk through some of this, okay? Let me see. What else? What else? What is that high order bit still the sign? I don't know what I meant by that. Yes, I did create these slides. No, I don't remember what that means. Oh, yes. Let's move on. I think we're going to get there. Okay, let's go back to some other two's complement tidbits. So therefore, what's the range of numbers? So we're going to say that this one is negative 128. Okay? So what's the range of numbers that you can represent with two's complement? And the range... What's that?
Negative 128. I don't think that's negative 128 all ones.
Is it?
If you flip all the bits, then it's all zeros, and add 1, that'll be negative 1.
You're right. Wait, what just happened?
So if you take 1 followed by all zeros, that'll be... I think that's what you're trying to do on the last slide.
Wait. No, you're right. You're right. That's the all ones is negative 1. Man, where did I go there?
So if you had a 1 as the sign bit followed by all zeros,
that's negative 128.
That's 128. And
Yeah,
I think that's
thank
what
you.
you're trying to do with your last point on your last slide.
Yeah, that's right. That's right. No, that's exactly right. No, I totally spaced. You're absolutely right. And there's also an intuition that just goes, all ones is negative 1, FF is negative 1 in hex, etc. Yeah, no, that was complete space on my part. Yeah, thank you. Thank you for that, for catching me. I'm going to have some more Oreos and whiskey and be back to you on the rest of this. Yeah, no, that's right. It is actually all zeros with the sign bit set. And I know that there's more coming here in the slides that it kind of articulates that.
So then with being the sign bit to 1 and the rest being 0, what would be all ones?
Wait, say that again. If the sign bit is set and they're all zeros...
Yeah, if the sign bit is set and they're all zeros and that's supposed to be negative 128, then what was the...
All ones?
All of them being, yeah.
Negative 1. Because intuitively, if I flip all the bits and add 1, right?
Oh, okay.
That's positive 1. And if I flip all the bits and add 1... Yeah.
Oh, okay.
Yep.
There you go. Gotcha.
Right. So the largest positive number remains, what's it going to be? It's going to be 0. That's going to be your biggest positive number, am I correct? I think that's right. That's going to be positive 127. Because, again, it's the same as sign magnitude, right? Or unsigned, if you will. As long as you're only using 7 bits. Sign bit has to be off to be positive. Then you just start tallying them up. 1s, 2s, 4s, 8s, 16, 32, 64. Add them up, you get 127. Right. And I think let's keep moving to... I think I've got a couple slides I'm remembering. So the largest positive number and the largest negative number is negative 128. So it's a little bit funky. Okay, so in fact, this is where we were going. I just did this with my hands, right? I really don't... There was like a brain seizure there. I think I just totally did brain seizure on that negative 128. My apologies. But there's 1. We flip the bits. We add 1. All ones, that's negative 1. Cool, right? We got that. Let's go negative 2. And somebody was actually in the comments, which kind of go by sometimes. I can't always see them in the window I've got. Actually questioned, I think, Andrew asked about negative 2. So let's take a peek at it. So there's 2. There's positive 2, right? And we're trying to figure out the negation of positive 2. We flip all the bits, which you can see. We add 1. 1 plus 1 is 0, and then the 1 goes like that. And I'm actually looking down to see what Andrew had said, which is exactly right. Excuse me. All right, so what's the pattern? The pattern is -1, there's -2, that's -3, that's -4. And this is my way, again, ignoring the little brain seizure from earlier. When you keep this party rolling, what's going to happen? Eventually, you're going to get to a sign bit and everything's 0. And that's going to be the biggest negative number, and the one that's not intuitive. All right? Everybody cool with that?
Makes sense.
Here's the thing. The fundamentals here, as I think you can kind of start to see, not that hard, not that crazy. There are a handful of little things to try to remember that are a little tricksy. Other than that, it's kind of straightforward. So the next thing you got to be able to do, also, by the way, time-wise, we're officially just past. We started a little late because I'm dumb. I'm not really dumb, but it was dumb. And I'm still trying to do better at that. What I'm going to try to do, I'm going to just go. Is that okay? I'm going to go for another 8 minutes, 7 minutes, okay? And then we'll be at a little more time, cover a little more of the material. If you got to go, just come back to the video. You know what I mean? Come back to YouTube and watch the last part. Is that good? Everybody kind of green light on that? Nobody complaining about that?
Go for it.
All right. Okay, right. And then Tyler raised the question, what happens when you flip all the bits and add 1 for -128? And it's freaking the same. It's like once you're on -128, because there's no negation. There's no representation for +128. It's freak. So you can't actually negate it. Okay. Here we go. So one of the valuable things you got to do is take a binary number and look at it and understand how to understand what the decimal equivalent is of that number. Okay? When we're in 2's complement notation, on account of social contract. So here's how we convert a binary number in 2's complement notation to decimal. Okay? Number 1, you got to check the sign bit. You got to check the leftmost bit. And really down here, if it's 0, easy peasy. It's a positive number. It's sign magnitude. Just add them up, right? How many 64s? How many 32s? How many 16s? How many 8s? How many 4s? 3s? 4s. 3. I said 3s. I have issues. 4s, 2s, 1s, right? Everybody cool with that? That's how you convert a binary number that's positive to decimal. And that's actually true of any positive binary number. That's how you do it. You just have to know what the value in each place is. And if you get it all confused, start at the right. 1s, 2s, 4s, 8s, multiply by 2. 16, 32, 64, 128. Okay. The dicey part is what if it's negative number? The leftmost bit is 1. Now what do you do? So the answer is there are slightly tricky ways that some of you will already intuit, that you can look straight at the number and kind of tell what the what the positive equivalent is. To me, it's a little bit funky. Oh, and by the way, this is a part of the book that I think is not great and maybe more confusing than if you just looked at the slides and then follow what I'm saying, except for the part where I blew -128 for about 2 minutes. Okay, if it's if the leftmost bit for you over here, if this bit is on, make it a random note. It's tough to do binary numbers with your fingers. You risk being offensive. You have to find socially because of. Yeah, okay, actually this is a perfect example, by the way, right? If I'm going like this, if I'm going like that and I raise these 2 fingers, what does it mean? Okay, well, it depends. If these represent binary numbers, it means, I don't even know, right? A 1, a 2, 4, 8, 16, 32, 64. It means 66 in binary. If it's not binary, the social contract, it means like double FU. Right? It means different things. Okay, but if I've got that bit set, I know I've got a negative number. To figure out what that value is, I can start by, frame the paper. I can start by writing a minus sign, okay? Start by writing a minus sign on your paper so you don't forget. Some of you are going to have like negative 83. And then you're going to go, okay, and you're going to do everything right. And when you're done, it's going to say, what's this value in decimal? And when it's done, you're going to write down 83. No, it's negative 83. So when you see the sign bit, and I'm asking you to convert it, step number 1, draw a minus sign so you don't forget. Now convert that number to positive. How do you convert it? Flip all the bits and add 1. Now that's the positive version of that number, and it's way easier to see the magnitude. And you go, oh, okay, 83. Boom, my number was negative 83. Everybody cool? That's it. That's all you do. Let's do one, shall we? Oh, actually, no. Sorry, that's binary to decimal. That's almost trivial. Okay? But when you go the other way, it's a little more tricky. What about decimal to binary? Like, let's say I've got 83, and I'm trying to convert it into a binary number. The fundamental question, this is, again, going back to my... Actually, if I did this and then flipped everybody off, it's hard on the hand position. If I did this and flipped everybody else off, it's actually not as obscene. It has to be this way. Why? We have social contracts, right? How about this one? Italians, I want to apologize. UT Austin, Texas fans, hook 'em horns. This is vulgar in Italian, in Italy. Okay? But it means hook 'em horns if you're a Texas fan.
Peace sign flip backwards, vulgar in England.
Vulgar in England, exactly. That's right. There's a famous picture of Winston Churchill doing this to the press, right? You know? Yeah. Think exactly right. Okay, yeah. And social contract. Okay. The fundamental question is, when I go like that and I give you some set of bits, the question is, sorry. When I say 83, the question is, how many 128s, how many 64s, how many 32s, how many 16s, how many 8s, how many 4s, how many 2s, and how many 1s. That's really all you're asking, is how many of these things. Does that make sense? Because the notation just says how many in each bucket. That's all it says. So I'm going to wrap this up and then I'm going to stop. So how many 128s are there? Bueller?
0.
Bueller says 0. Okay. Yeah, so there are no 128s. How many 64s are there?
At least 1.
No, there's only one.
Oh, there's, yeah.
Because binary, right?
Yeah.
So, yeah, that leaves, so we got 19 unaccounted for. We have 19 that we didn't put in buckets. How many 32s are there in 19? None. How many 16s are there in 19? 1. 3 left to go. How many 8s are in 3? None. How many 4s are in 3? None. How many 2s are in 3?
1.
And then we're left with 1. How many 1s are in 1? 1. Boom. That's a binary number. Now, in this case, we're not worrying about whether this is, it's a positive number, it's 8 bits, we're just, it's unsigned. It doesn't really matter at this point, okay? Everybody cool? That's the process. So it's a little more cumbersome. But what do you do when it's a negative number? Decimal number. There's really only one trick.
Take the positive, make it positive, and then flip it, add 1.
Yep, that's right. Just do the positive version of that decimal number. Then negate it once it's binary. Okay? So in other words, that's it. You find the representation of the positive version of that number, then you do the 2's complement negation. You do the negation as, 2's complement, and that generates its negative. And then Andrew suggests, if you like, by the way, if you have little tricks like this, like Andrew is enticing you to think about another way of doing it, great. I'm only going to teach you just this one way because I think it is literally the most simple way, and it's easy to remember, and you can, it rests on the fundamental idea of what the notation means in the first place. But if there's some other tricks and you want to use them, knock yourself out. Totally good. Okay, we're going to stop there. We're on this one, operations on bits. We're going to start doing math. And we'll do a few things. By the way, just FYI, we are on slide 59 of 92. We're going to talk about math operations. I'm just looking, you can't see it over here anymore. But we're going to do math operations, and then we're going to do bitwise operations, and then we're going to talk about hex and ASCII. We should wrap that up on Thursday. All right. That is it. Let's wrap up. And thanks for being here today. Great questions, great gifts, great memes.
Baby Mimi dreamers.